everybody for joining. Today we'll have Christian from Quantum Brilliance. He'll go over his their workflow at Quantum Brilliance, and yeah, I'll hand it off to you.
Thank you, Amir. So, hello everybody. My name is Christian Ortiz. I'm working at Quantum Brilliance. I'm a member of the software and applications at Quantum Brilliance, but I'm also working on HPC integration. Here at Quantum Brilliance, we have developed a tool that we call the Quantum Q utility, and that's what I will discuss with you. Of course, before talking about the tool itself, I just want to give some brief introduction about the company. As you may know, there are 8 leading approaches to build a commercial quantum computer. And as you can see in the diamond defect section, that's where Quantum Brilliance is. So we build our quantum computers at room temperature, considering defects in diamonds. Currently, we have our main offices are located in Germany and Australia. That's where we build the chips and build the quantum computer. But we also have offices in Japan and UK, for example. Now, here I'm listing briefly the research areas within Quantum Brilliance. For instance, we are working in quantum sensing. We are working in the pulse level access. We are working in algorithms related to our defects in diamonds, and as well in quantum accelerators and the quantum development kit, which is what we call the QDK or what we generally call the quantum computer. And we are also working in a field called the mobile quantum computing, which is an extension of the QDK, but it becomes more flexible, basically. So this is the roadmap at Quantum Brilliance within the last years. And here, what is important to note is that we have installed quantum computers in 3 HPC centers, and all these 3 centers use the Quantum Q utility that I'm going to discuss today. In 2022, it was installed at POSI in Australia. In 2023, the quantum computer was installed at Fraunhofer IAF, located in Freiburg, Germany. And we installed 3 quantum computers at Oak Ridge. Of course, our goal in 2028 is to shrink our device because currently it has the size of a compute node, but we want to make it the size of a GPU. Okay, I think we can jump now into the quantum HPC integration. What is next? And this is a question actually coming from Quantum Brilliance itself. I mean, within our goal that we look in the coming years, what is next for us in terms of quantum HPC integration, right? And for that, basically, we have divided, for us, there are 3 main levels for this integration. Level 1 is the most general, or the first level where you have a facility-sized quantum computer in one room, not necessarily close to the HPC system. And of course, you have the HPC system on the other side located, of course, in a different room. And then you use, for instance, Ethernet or InfiniBand cables to communicate. Now, that's level 1. Of course, Quantum Brilliance currently has the experience in level 2, and that's where we are. And I'm sure that a lot of companies are actually in level 2 as well. And that means that you put within the same room, basically, you put your classical racks and your quantum racks. And of course, you may have as well hybrid racks. And one example is, of course, there is a picture here of one example where we have the 3 quantum computers in one single rack. And currently, Quantum Brilliance is using this type of systems for ab initio chemistry and optimization applications. And of course, when you put the quantum computer close to an HPC cluster, you need to take into account, for example, the electromagnetic isolation that your system needs, or vibrational isolation. And if you work with low temperatures, the cryogenics, right? So there are multiple things that you need to pay attention when you try to move the quantum computer close to the classical racks. And of course, we are aiming for level 3. That's our path. And that means that within a single node, actually, you may have hybrid components, I mean, classical and quantum components. And you see on the right-hand side a picture of what I mean. For instance, within a single node, you can, of course, if we successfully shrink the device, we can put the quantum accelerator as via, for instance, PCIe connection, similar to what we do currently with GPUs. So that's level 3 for us, and that could be used for molecular dynamics, machine learning applications with parallelization, and so on. And the advantage of level 3 is that we will use just the classical compute infrastructure. That's the goal, to really just use the classical compute infrastructure. So that's basically what we see regarding the quantum HPC integration. Now, of course, in the process, we have developed this tool called the Quantum Q utility. And for short, we call it QTIL, and that's how I will call it in this presentation, QTIL. But I want to start from the basics, right? Just to give general information first, and then complexify the information with the coming slides. So this is how, well, that's how Quantum Brilliance quantum computer, or QDK, works. Most working a similar way. And the main idea, of course, here I'm disregarding the fact that we are in an HPC cluster, right? That's the basic idea, where you have your laptop, the user has a laptop with the client SDK, and then you have the quantum computer. The quantum computer, or the QDK, actually has 3 components. One is the software component that we call it the QC stack. Then we have a second component that I didn't put an icon there, but it's the control system component. And then you have the quantum chip. And the communication is via REST API. It's the most common communication. So the idea is, in this simple picture, is that the client just sends information via via an API call to QC stack, the software. The software takes that information and then transfer the information to the control system, which includes in our case, the radio frequency system on chip, sensors, actuators, electromagnetic sources, and so on, right? There is a communication of the software with the control system, and this control system is the one that interacts with the quantum chip. So in our case, this software does a lot of things: transpilation, optimization, calibration. It also does scheduling, of course, because if you have multiple users just sending a job, then QC stack will receive that information and will choose which one goes first. And of course, in this case, it's most likely that one job needs to finish in order to start the next one. At least that's how it works, our QC stack. But of course, there are multiple issues if you just rely on the software within the QDK. And that's why we need to implement additional tools to optimize our scheduling and basically the reservation of the quantum computer. And that's where that's how we came up with this QTIL tool. And the goal of QTIL is to reserve the QDK. And now I'm complexifying the system here. It's not just the laptop, the user laptop, and the quantum computer, but now we are putting an X node in between. In an HPC system, this X node could be the logging node, could be the compute node, could be what in other presentations you refer to as the quantum gateway node. But the key idea here is that in this intermediate node, if you want to use QTIL, you need the two components, right? You need the client SDK and you need the QTIL component. And the QTIL component, in our case, works with a database, because information is stored in the database. So the main idea is that without taking into account Slurm, without thinking of more complex things, just thinking of Qtil plus SDK installing a single system, the user first needs to use Qtil to make a reservation, right? And once the reservation is accepted by QC Stack, then any information coming from the client SDK will pass through this reservation tunnel, as you can see depicted here with the arrows. That's the core idea. That's the main idea. In previous presentations, we have heard about this QRMI, QDMI. Well, Qtil is basically a quantum resource management interface. And now, how Qtil works. Please keep in mind that so far, first, I will explain Qtil, how it works without any workload management tool, just Qtil on its own. So that's the first step. So how Qtil works, there are two steps. The first step is to register devices in the database with their own API secret keys. That's done by the admin. And of course, we need an admin, we need a closed system where the admin can have access basically to these secret keys, and he can allocate the keys in the database. And this is an example of the database, what fields the database has. Just to give you an example, for example, we are naming here multiple devices that we registered in the database. We have 3 QPUs, 3 quantum computers, and 2 virtual quantum computers, because you can as well allocate emulators if your emulator is built with REST API as well, right? If you have emulators with REST API, you can as well include them as a device here, and that's why we have as well virtual quantum computers. Now you need to add the address, the IP, and the port that you're using. And we have a specific field called the Q field, and this is one way for you to choose or to group devices according to similarities or whatever you think it's important to group them. In this particular example, for instance, QPU2 and QPU3 belong to the same queue, the QDK2 queue. And ARC actually refers to the device, because the idea is if we want to scale this, you can choose a different company. For example, instead of Quantum Brilliance, you can put IBM, Rigetti, IonQ, whatever, right? The ARC is just to differentiate between quantum computer companies. The secret, as I mentioned, is the secret key, and the status gives you what's going on in this precise moment with this device. There are commands, of course, that come into play. Well, in step 2, we are going to focus on the reserve command. I mean, this is the register, the remove command. Of course, the first two are only admin, are only accessed by the admin, but the reserve and release are accessed by the user. You don't need a special password to access these commands. And on step 2, I'm showing you one example of how it works. So if you want to reserve a device as a user on your terminal, you just type the command, the Qtil reserve with specific flags. And in this example, I'm using 2 flags. Of course, there are additional flags that could be added and exist actually. But in this example, I'm showing 2 flags, the Q flag and the duration flag. And as you can guess, or you can infer from the command, you already know that, for instance, this user is trying to reserve only QPU2 or QPU3 because both belong to the same queue. So, and what you can see is that because the status of QPU3 is reserved, then you can guess that what will happen is that this user will get allocation only of QPU2, right? Because that's the one that is status normal, means that it is free or available. And the duration is, in this example, is for 60 seconds. After 60 seconds, the reservation is removed. This is, of course, an exclusive reservation. Now, the steps of Qtil are given below, as you can see on the rectangles. The first, Qtil will parse the CLI arguments. Then it will decide when to start or end the reservation, because you as well have flags for this if you want, of course, additional specifications. Then it will pick the device. In this example, it will go through to the database. In this example, it will grab the QPU2 as the available device, and it will create a JSON Web Token. And this JSON Web Token, based on the secret key, of course, will be sent to QC Stack in the QDK. And of course, QC Stack will validate this JSON Web Token. This will pass through this API reservation endpoint. And once the QC Stack validates this JSON Web Token, it will create a session, and the JSON Web Token will be printed on the terminal of the user. Note that we are not speaking of Slurm yet. So basically, if we think about this user, once the user gets the JSON Web Token printed on the terminal, then he or she should manually copy that token and paste it on whatever code he's using with his client SDK. So that code will have the JSON Web Token, right? That's how it works. Of course, now you can see a problem there. You will think, okay, yeah, that's a bit boring to all the time just copy pasting the JSON Web Token. And that's why we go one step forward and we go into Slurm, right? Now we use the workload management tool. Qtl with Slurm. Now, here I want to make a brief, I want to mention something about what I heard in previous talks, because in previous talks, we discussed the fact that mainly there are two approaches for quantum HPC integration. On one side, we have this GRESS approach, and on the other side, we have the license approach. And for example, regarding the GRESS approach, we saw that you can do it by installing the Spank plugin. And well, actually, Qtl is based on the license approach. So I think this is the first talk regarding a license. I will show you what's about, right? So I'm just giving you a picture here of how the integration of Qtl with a Slurm works. And the idea now is that in an HPC system, the user will have in this example, I'm showing a Slurm. It can work with a different workload management tool as well, but the example is with Slurm here. So the user create a batch script, the S batch, and it goes to Slurm. Then Slurm will grab that information, and this job information will be sent to Qtl. Then Qtl will make a reservation, will check if it's possible, of course, and then once it makes the reservation, as I mentioned in the previous steps, it will send the access token to the node where the client SDK is, because Slurm in the process will do also a classical node allocation if needed, of course, and usually when you work with client SDKs, it is needed. But if you send, for instance, direct openQSE scripts or circuits that are fully understood by the QDK API, then you may not need the client SDK. But in this example, of course, if you need a client SDK, this client SDK is locating a classical compute node. So Slurm will allocate this compute node, and the access token of Qtl will send the access token, the JSON Web Token, basically, to this client SDK node as a shell variable, meaning that the shell variable will automatically be, if your client SDK, of course, is configured correctly, will automatically grab this shell variable, and then the user no longer need to copy or paste the code. It will be all basically within the client SDK code. And that's one advantage of using Slurm, because then you ignore copy pasting, as I mentioned in the previous slide. Now, of course, we have additional features such as the cron job that will check the status of the quantum computer. And of course, then once you have access to this classical node from the client SDK, you can send circuits or pulses, depending on what you do, to the quantum computer or to the virtual QPU, as I mentioned previously, because it works with emulators as well. Now, just to give you an idea, if you are not familiar with the license approach, Slurm, this works with the Lua plugin. And usually when you submit your SBatch, you need to add a flag called the -L with specific parameters regarding the allocation of the quantum computer. So that's how it works. If you add a flag to your SBatch submission, then you are able to send information, parameters of your quantum computer to Slurm, and that's what I call here the job information, because the Lua plugin will process those variables and will convert them into Slurm environment variables that will be afterwards understood by Qtil. Now, that's actually the presentation. I wanted to make it very short. Maybe we can have discussions afterwards. And maybe just before finishing, what I want to mention is that this is a license approach. I don't know if there are others that will also speak about a license approach, but if that's the case, it will be nice to create a working group regarding this approach, because then we have the similar we have working similar stuff, so we can build a general conclusion from that perspective. Well, thank you.
Thank you, Christian. Any questions? I have some, but I'll open it to the floor. Go ahead, Yush.
Thanks. Thanks a lot, Christian, for the presentation. A couple of quick questions on the initial sort of the standalone queue that you have. Is that still a FIFO queue that you manage, or is it a priority queue? And then, so what are the sort of features that you offer for the standalone one?
You're on mute, Christian.
What are the features that I offer to whom? I didn't get the last word.
No, for the standalone queue that you have, the one that does not integrate with the workload managers, is that the standard FIFO queue that you have that you support?
Yeah, you mean the Qtil tool?
Yes, the Qtil tool without a workload manager.
Yeah.
Or is there a queue, right? Is it that you submitted, if it's available, you get it. If you don't available, you said you have to try again later?
Yeah, that's how it works. Yeah, precisely, that's how it works. You submit your reservation. If it's not available, it won't reserve, basically. But also you can get the information in real time as a user. You don't need to test a reservation, because in real time you can see if it's already reserved or not, because there are additional features that allow you to get the real time status of your QDK. Mm-hmm.
Got it. And for the Qtil with Slurm, right? So if you want, let's say, a set of classical nodes along with your QPU, meaning how do you sort of ensure that Slurm can reserve both successfully, right? Will Slurm be querying the real-time status of Qtil and then see if it is available, the QPU is available? Then it will reserve both classical and quantum together, or how does the consistency work across these two systems?
Yes, it first needs to check if the quantum computer is available. If it's not available, it won't allocate the classical node. It's the priority is the quantum computer. Mm-hmm.
Got it. Yeah, and so let's say I can see boundary conditions coming up. Right, there's almost like a two-phase commit in a database that can come up. Right, so are those sort of boundary conditions taken care of? Let's say the QPU is available, but the so it'll check both and then figure out if both are available, reserve those successfully.
You mean if the user wants to reserve multiple QPUs?
I mean, I'm just trying to understand, because you got pretty much two different systems, right? One for the set of classical nodes and one for the quantum. Mm-hmm. Let's say I check the quantum, it's available, I reserve the quantum, right? But in the meantime, if the classical is not available, will I end up with issue, like edge cases like that?
In that case, of course, in that case, let's suppose the quantum computer is available. Of course, it will make the reservation, but if if the classical node is not available, it will happen what usually happens with a Slurm, right? You are in a queue, you don't get the reservation, you don't have access to the client SDK, and of course, in that case, the reservation of the quantum computer will stop. Will not continue. Will stop. Because the only way that you get full reservation access is both need to coexist in our case.
Right.
I mean, it will first check the QDK, but then it needs to go to the compute node because it will submit the JSON web token to the classical node. But if it does not send the information for any reason because there is no allocation, then it won't fulfill the whole process, basically. Mm-hmm.
Okay, thank you.
Go ahead, Jeff.
Hi, thanks, Christian, for the very interesting presentation. It's a fascinating way of. I like seeing, how you put this all together. I think it makes a lot of sense. I was kind of curious about one of the nit details. You sort of said like reservations are about 60 seconds. Is that sort of the general time frame that you expect? Or is this something where people will go longer or shorter? And sort of what timescales do you see people using this?
No, of course not. I mean, reservation. There are calculations at least with our QDKs that take more days. It's not that was just a simple example. The truth is that it won't be in seconds. It will be in hours in some cases. So. Okay. Now, just to, of course, this is what I'm showing here is like, we can call it like a general introduction to Qtl. You can complexify the tool. You can add more fields in the database with restrictions to the time needed for reservation and so on, right? But yeah, that was just a simple example.
Okay,
yes.
Thank you.
So I wanted to piggyback on Yogesh's question. So when you say you reserve both the classical and the quantum, are you using some Slurm feature like the heterogeneous allocation to like manage the multiple reservation at the same time, or do you implement your own logic or add some sort of logic that allows you to do this type of concurrent reservation?
No, it's our own logic within the Qtl tool. Slurm is only used for the classical allocation mostly, and we grab all those informations with the Slurm variables. So in the end, if the classical node is allocated, then Qtl will be aware if that was successful. Mm-hmm.
Okay. I have other questions, but if anybody else wants to. All right, I'll raise my hand again. So the reservation, when you go, sorry, I'll unraise my hand and I'll let Hiroshi go. Go ahead.
So sorry. Yes, I mean, Miss, I did not catch up the middle of your talk. You mentioned that QRMI, but QRMI, and then also you are using the license approach instead of GRASS. But I guess GRASS approach is can be also integrated with your Qtl approach by implementing the Spank plugin or something. Is it correct, or do you have any plan to extend your work to or GRASS or approach?
That's an interesting comment in the sense that I personally have not thought about it. That's why I suggested if there are more license people working with the license approach, it would be really interesting to have a further discussions if what they have in mind, right? If they are actually planning what you just said or not, and that's something to be discussed afterwards, actually. Mm-hmm.
Thank you.
Piggybacking over that question, you mentioned in, I think, the second or third slide, you said Qtl implements the QRMI. Did you mean that literally, like it actually implements the API that QRMI, the IBM implementation of QRMI exposes, or is it like you're using that term differently?
Yeah, maybe it was not clear. Yeah, I'm just using that term. What I wanted to say, we are more like this QRMI approach, but we are not exactly what IBM has been doing, right? Mm-hmm. Yeah.
I have more questions. Anybody wants to jump in? Okay. Can you go to the very first slide where you show the roadmap to the the card when you go miniaturize and you become like almost like a GPU style card?
Yes, just a second. I don't know why my screen froze. I will just stop sharing and reshare again. That's interesting. Did you see my screen closing?
Yeah, closed. It doesn't matter. I can just ask the question.
Oh, okay. I can share again. Yes. Yeah. Okay. Which one? This
The
one?
number 3, I think. No, number 3, slide 3. Yeah.
Yeah.
So when you get to that, I was wondering, do you know how the qubit control will occur? Because right now you have, you know, in the QC stack, you mentioned a bunch of things, including the control of the qubits themselves. Will that control exist on that card, or will it be like on a separate node that controls the card?
Yeah, I mean the goal, of course, is that it could be within the accelerator. That's a big goal if we think about it, of course. But the process will be in steps, right? It's not that directly we are just putting everything within a GPU size this system. We will just go in steps. We first will put the qubit in, but not the control system, but maybe as time goes, we will always try to merge them.
Okay. So for a period, the control will exist outside. So can you go to slide 7? Sorry.
This one?
Yeah. I was wondering then the QC stack here, that's right now, that's where the control is, right? Like where the software that does the control of the qubits is, right?
QC stack is the software.
Right, and it exists right now on the box we have at Oak Ridge, for example. It has, you know, the blade that is classical with CPU and GPU, and then the QPU as a different blade. The QC stack right now runs on the classical part of the node that we have here.
Exactly. The classical part is QC stack plus the control system. And the quantum part, it's just the whole the physical system, that chips, the lenses, and so on.
I think that's so. Then when the execution happens here, like when Qtil reserves this, you showed the reservation APIs, but like how is the running, like is there specific APIs in Qtil to actually run a script or run like pass a CASM file or something to run on the machine?
Yes, actually, in this example, for example, here in this picture, you actually, okay, you can use what I call the SDK here, over here, but you can directly send a curl command with a specific openQSE circuit line, because QC stack in our case understand openQSE directly, so you don't need a client SDK. If you know your OpenQSE circuit, you don't need an SDK. You just use curl and submit your API.
So there's a port that's listening that you can submit this work
Exactly.
to. Okay.
Yeah. We had multiple ports, and one of them is the OpenQSE. Yes.
Okay, so there is like, depending which port, one is dedicated for openQSE and then the other for other for the REST API.
No. It's if you speak of the port number, no, it's the same port, but we have different extensions within our API to manage that.
And then when it's received, then it goes and does all the trust violation optimization, and everything else happens on the box directly, right?
Yes, yes.
Cool. Thank you. That's all my questions. Go ahead, Luke.
A quick follow-up on Amit's question. So we got multiple QPUs, right? With the transpilation for all the circuits, or all of them happen the same sort of classical blade, or are they sort of paired up together?
What do you mean? If I have multiple QPUs, they will be independent, or what do you mean?
Right. So I'm just trying to understand where the control system runs, right? And also the QC stack. Are these on a single classical node managing the QC stack and the control system? And if you got multiple QPUs, will that become some kind of a bottleneck for transpilation and so on?
Yes, but in this particular, our current quantum computers is a set of one QC stack software plus one control system plus one quantum chip. That's what we currently have. So multiple QPUs within the same QDK, we don't have that.
Okay, so when your qtl command is executed, it's independent, and you got queues that are there. They are independently talking to the different these units that you're talking about, independent QPU units.
Yes.
Okay.
Yes.
So qtl sits a layer above your QC stack and the control, right?
Exactly. Yes, that's how it works. Yes.
Great. Thanks.
And for the qtl, when you have like when you say reserve -q and then you specify that queue name like QDK2, here you're not really specifying I want one QPU or two QPUs. Is it just defaulting always to one QPU? Like
no. Actually, you can choose multiple QPUs at the same time. It's just that I made a simple example. We have an additional flags for the number of QPUs that you want to reserve. And that's why, I mean, there is a small here where it says for multiple devices, reservation is concurrent based on Go functionalities, because Qtl was built using Golang.
Okay, so in the example that you have here, if QPU 2 and 3 are both using QDK2, then in your command you can say I want two QPUs, and then if both of them are available, then you get that reservation?
Yes, and as far as I remember, the flag is N for number -N2, and it will look for 2, and if it doesn't find 2, it won't give you the reservation.
Thank you. Anybody else has questions? Go ahead, John.
Yeah, sorry, just one other technical note. I'm not particularly familiar with Slurm, and I was kind of curious about the license versus, I think you said, graph model.
Gress, yes.
Gress. What? Can you elaborate on what that means?
Yeah, the Gress is what you usually do with GPUs nowadays, when you allocate a GPU, you use this GRESS configuration file. And that's how you can choose a specific GPUs that you want to reserve. So that's one approach. And Qtile approach or the plugins related to Slurm are based on the license model, the license approach of Slurm. So instead of using this GRESS configuration file, you just used what is called a job submit.lua file, which is a file that will read whatever you put in your license flag when you submit your Slurm sbatch command. It's just like this command. For example, here you do qtile reserve. So in Slurm, you will do sbatch -L for license, and you will put parameters that will be understood by the job submit Lua file.
Okay, thank you very much.
General question to the audience that might be more familiar with Slurm is, does GRESS not support license? Like, are they completely two separate features? If you use GRESS, you can't use licenses, or is there a crossover? I don't know.
Well, Hiroshi actually mentioned the possibility if we are thinking of trying to merge this license with the GRESS approach, right, Hiroshi? I mean, that's something that I did not think about, but I don't know, maybe he's more familiar with that. I'm not familiar if it's really straightforward just to mix them up.
That might be a good thing to look into, I guess. The other thing to throw out there, underneath the covers, Qtile implements its own stuff. Have you guys looked at all at like trying to at least match the API for QRMI or QDMI in some form? Is that something that you have on your roadmap?
No, we haven't, but these presentations are giving us some ideas about it, actually. So that's good. That's why I'm very interested in hearing a presentation that may have worked with the license approach as well, to understand what they have done right.
Thank you. I don't have any more questions. Anybody else got questions? Going once, going twice. All right. Thank you, Christian, very much. That was very good. If you don't mind, can you send me the slides? Is that okay?
Yes, it's okay.
And it's
Yes.
okay to put it online, the video on the.
Yes, it's okay. It's okay. That's why I try to make simple examples in these presentations so it can be publicly available.
Awesome. Thank you so much. Thank you,
Yep.
everybody.
Thank you.
All right. Take care.
Thank you.
Bye.
Thank you.